You might have noticed that this whole subject of mechanics is about statics, right? But then there is a chapter on kinematics and kinetics of a particle. Now, but this involves motion, that is, something is changing with time. Now, then why is it so? Why in a subject on statics we have this topic of motion? The point to be emphasized is the term particle. Okay. Now, when we say kinematics or kinematics and kinetics of particle, what we mean is that particle could be the center of mass of a body also. Okay. Then, so basically we will be dealing with acceleration in a way. Okay, and that could be the acceleration of the center of mass. And if means, let's say, suppose there is a body, okay, and its center of mass is lying somewhere here, and if this body is subjected to some forces in some arbitrary direction, now it will have a general motion, right? So it may move, means it may translate and it may rotate. So we will be discussing a theorem called Chanceler's theorem, which will tell that any general motion can be in fact any general motion can in fact be split into a translation, a pure translation. That means you will just shift this thing somewhere plus a rotation. Okay. So that's how any general motion can be split into, and not only in 2D but also in 3D basically. Okay. In 3D also any general motion you can think of it as a translation, then a rotation about some arbitrary axis of rotation. Okay. So that in 3D it's very difficult to even visualize that. We will see how to visualize, but then in 2D it's easy to see about what point we were rotating and that thing. Okay. But then if we just for a moment forget about the rotational part, okay, the rotational aspect we just don't think about, then the forces which are acting will try to cause this body to translate. So this body will have a linear acceleration. Okay. Now in that case we can assume that this full body to be concentrated at that particular point, and the whole of the force forever in whatever direction they are acting, and they are causing the acceleration of that particular point. And then if we can do that, then in fact even if it is in motion, so we can write the equation of in a way balance if we consider the pseudo forces. Okay. So that means so F is equal to ma. Instead of that, if we just use the pseudo force in place of the actual acceleration, we can write in this way also. Now this becomes a balance equation again. So in this case we can say that everything is in static. So okay, so dynamic equilibrium, equation of dynamic equilibrium, and then if we know this acceleration somehow, so if we just multiply with m, we get the pseudo force which we can consider to be acting along with the F, and to keep everything in balance. Okay. Now, so that tells us that somehow if we can know about acceleration of the center of mass of the particle, then a lot of things can also be told about dynamic equilibrium as well. And from that perspective, I feel that okay, so this topic of kinematics and kinetics of a particle are fine they should be in this subject of statics. Okay. Okay. Then one more point which I wanted to make is there are two ways to look at this equation. Okay, F is equal to ma. There are two ways to look at it. One is knowing the force, can we calculate the acceleration? So in fact, from that the two terms, the kinematics and the kinetics, so there is a little bit difference between them. So that basically is the crux about the difference. Now if you are thinking about the reason, the cause of the acceleration, then you are thinking about the kinetics of the particle. But if you are just thinking about the geometry of the motion, then you are talking about the kinematic of the particle. Okay. So now if force is given and you have to figure out the acceleration, so that's one way to see that. That means in that case you will write A as, you know, so dr okay, d2r by dt square is equal to say 1 over m times f. Now if f is known as a function of time, then you can always integrate and find out how r is moving. So r as a function of time. So that is the output which you will look for if you see from this perspective, that is, given f, can I calculate a? So that is one way to look at it. So that is the kinetic part of it. And then there is another way to look at this equation is, given acceleration, suppose we know the acceleration of the particle, then we can think of how much force actually is acting on it. Okay. Now that is basically the kinematic part. That means if we know the geometry of the motion, that means on this path, for example, I am saying, suppose there is a given path on which there is a particle which is moving. So this particle is moving on this path. For example, suppose there is a car and there is a road on which it is moving with varying speed. Okay, the speed may not be constant. Say the speed is changing with respect to time as a very arbitrary function of time. Still, at every location in space or every location in time, we can calculate the acceleration, and then we can also infer that just by multiplying with mass, we can tell that how much force is actually acting on that particle. So these are the two ways to look at these this single equation, and in this whole thing we are neglecting the other part which is like, you know, so the torque is equal to I alpha sort of thing. So that we are not at all talking about, because this involves a lot of other things. See, this will become a tensor, and these are vectors, and the equations which we will get, they will be in a way coupled, the differential equation, you see. So here it's the equations are not coupled, so that is why the solving this differential equation to get this displacement as a function of time is quite easier than solving this and to get the angular displacement from this. So this part we are not at all discussing, and we are concentrating only on this kinematic of the particle, so that directly from the geometry we can say what is the force, and if we just multiply with a mass which is a scalar, we can talk about the force. And then this simplification of analysis is not possible when we go to the angular quantity, the angular velocity, angular acceleration, the torque and the moment of inertia, everything, because everything becomes complex just because the reason that here the mass is a scalar, whereas this moment of inertia is a tensor. Okay. Now Having said that, we are now fixing up our stage that our main job, primary job is to talk about acceleration basically. Given knowing the geometry of the motion or similar such properties, our job will be to find out acceleration. So you can say that this is the topic about acceleration. So let us see you in the next segment, where we will start discussing about various coordinate systems. In fact, we will be talking about types of different, we will start with 1D, then we will go into 2D, then 3D, and in all such cases different types of coordinate systems are much more useful than some other type, and we will discuss about them, and then we will later on we will go to relative velocity. Means suppose two bodies are moving with respect to each other, then how they see each other's motion and how to take differentiations of vectors from one reference frame to the other. All those things will come up and then we will see them in segment to segment. Okay. So, see you in the next segment then.